Hello everyone, and thanks for joining a talk about cars, code, and community. And hey, if you came from the snack and stay for Linux, we are already friends. But since this is an open source summit and you're willing to walk into a talk with automotive in its title, that says something. Either you already matched and wrestled with some Linux for automotive, or you're just curious to know how it gets so weird. This session introduces AutoSD, its development framework, and how it brings cars into Linux. So now we're introducing the speakers.
Okay, I'll start with myself. I'm Gabriele Paoloni. I work for Red Hat as a senior principal software engineer, and I'm also pretty active in the Linux Foundation ELISA project, where I serve as governing board chairman. So most of you already know me. But I'm here today to talk about AutoSD. And today I'm wearing the red hat rather than the ELISA hat. However, we'll explain how this can be used and useful to ELISA as well.
And I am Alessandro Carminati, principal engineer at Red Hat, TSC member in ELISA, and also lead the Linux feature working group in ELISA. And I'm not the subject of this talk. So let's move on. Today, we are taking a ride through AutoSD. And no, this is not just another Linux distro crashing aimlessly in the open source lane. This one actually has maps and seatbelts. And here's the ingredient for this menu for today: a Linux distro, a tricky hardware, and a well-dressed cuisine. Here's the dishes. So, say in section 1, not just another distro on the highway. We'll see one of the most obvious questions, which is, what is AutoSD? And hopefully, at the end of this section, we will be able to answer it. Section 2, new hardware, no panic, because of course the hardware never matches the datasheet. And we'll see what works out of the box and what needs to be hacked, and how to survive to a BSP without losing your warranty, or your sanity if you wish. Section 3, why AutoSD fits automotive. And here's where we prove that AutoSD is just cool, it is safe. Containers, BlueC, and other friends will show up here. In the section 4, we will see the AutoSD calls cousin, where we see why it is having such a big impact on the AutoSD. And so, let's start. Now, that's an highway, but not your average Sunday drive. Imagine a modern software for automotive. It is tangled, it has lanes, speed, and unclear signal. To give you an idea, it's like commuting on Rome Grande Raccordo Anulare on Monday or Tuesday morning. You are on your own. Enter the AutoSD, bringing order in the digital road, but not let the word distro fools you. It is not just another throw on the USB stick distro and hope for the best. AutoSD is built for the road, literally. It meets particular needs for automotive system. It includes functional safety, long life cycle, and just not randomly reboot at 130 kilometers per hour. So in this section, we are going to pop the hood and see where AutoSD fits the ecosystem and what makes it important. We also cover its feature and strength, why binary, and why this is good, and what tools come out of the box. And the bottom line here is, if your car is going to run software, AutoSD is the distro that wants to drive. Let's talk about AutoSD. It might sound just another Linux variant, maybe something you find on an old USB stick, but AutoSD has much bigger ambition. AutoSD stands for automotive stream distribution and is being built from CentOS stream automotive SIG. And here's the fun part. AutoSD is the upstream for something that Red Hat is cooking up internally. A commercial-grade, safety certifiable in-vehicle OS. It is called Rivos, or how they want me to say Red Hat in-vehicle operating system. But let me say, Rivos is shorter, and it also sounds like a Marvel villain, so it makes it cool. But let's see how this proceeds. Anyway, why does AutoSD matter? Well, if you think of CentOS stream as the REL public staging, AutoSD is the same for your car. It is the early access preview of what eventually become Red Hat commercial in-vehicle OS, and this part is the key. Your patches, your feedback, your headache, and even those "why does this break on this board" GitLab issue, all this shape AutoSD. Got a new board that is not supported? Submit a patch. Found a missing doc? File a PR or open a PR. The community door isn't just open, it is automatic. Now, there is a phrase in tech we like to throw around: eat your own dog food. Well, not the most appetizing image, I guess, but the idea is use what you build. And Red Hat is doing exactly this, and you are invited in the kitchen. So, if you ever want to influence the next generation of in-vehicle OS, AutoSD is where this magic happened, and the best part is that the doors are open. Now, let's take a quick look on what makes AutoSD worth your time, your attention, and maybe even a second cup of coffee. It has declarative builds, use YAML to define your image, customizable container, AutoSD is tweak-friendly, OSTree and updates. With OSTree, updates are automatic and rollback friendly. CI and docs, you get stable documentation and support for CI workflow. You also have pre-built image. Don't want to build from scratch? Grab a nightly image and boot it up. Mixed-criticality. Run safely critical apps next to your infotainment. Easy and peasy. No chaos. So far, we've seen what makes AutoSD and what it's after, but why it is a strong pick for automotive development. I can say that standardization and pre-built package, you don't need to compile the universe. Update, security, and sanity are all handled upstream. Upstream for Red Hat in-vehicle OS. What we use today becomes Red Hat in-vehicle OS tomorrow. It is not a toy project. It's a real pipeline here. Open contribution model, got patches, feature, where bug at 2 a.m., contribute. The community part is part of the engine. OS build equals simple builds. Thanks to OSB, creating an image is like stacking Lego. No deep diving into the source tree, reproducible, modular, and sane. Build for automotive, not just embedded. Real-time, mixed-criticality, long-term support, AutoSD knows the road. It's built for this. So, why binary distribution? It may sound a bit corporate here, right? But hold up, because this is not the value of the story. Yes, you could compile everything from scratches. You could also churn your own butter, assemble your machine code by tables, or wave your own Ethernet cables, but point is why. With binary distribution like this, you get faster onboarding. No need to climb the mount, make file, you just need to boot. You skip the reinvent RPM wheel. It is already round and spinning. You gain predictability, same package, same behavior, unless your YAML is hunted. So, best of all, we have that maintenance and security are all handled upstream. You just ride the wave and let the upstream team tame the bugs. So no shame in starting from binary. It is not cheating. It is efficiency. And since you are not stuck in building from scratch, let's take a look on what gives you out of the box and how to customize the build. Okay, so we decide to live a live binary distro life, and we bug the box. What do we actually get in there? First off, meet the automotive image builder. It is the engine behind the magic. It is YAML driven. You declare what you want. No need to write your own image widgets from scratch. You can define what type of image you need, what package goes in, wherever you want container support or not, all clean and readable in YAML. The build runs on container, which means reproducible, portable, and free of all those, but it works on my laptop drama. AutoSD support OSTree. That means automatic updates, safer rollbacks, and fewer headache when things go sideways. Now, what if you want to swap something out? It is a good question. Just add a package, tweak a module, and sneak a pet project, for example. Let's talk about this. Now, so we've seen how OSD makes things easier by giving a ready-made package and clean image out of the box, but you might be wondering, wait, does it mean I can touch anything? Absolutely not. AutoSD is open, and that means that customization is not only possible, it's blessed. Let's say that you want to patch a package, test a driver, or just change something that bugs in you. You don't need to rebuild the entire universe. Just follow the classic RPM dance. Grab the source, tweak it, rebuild in a package using tools like mock, put in your own repo, and plug that in by change a few YAML line in the image. That's it. Your image, your rules. No source distro pain, no compile until midnight lifestyle. This is where AutoSD shines, ready out of the box, but open all the way down. Now, this is the part where many developers start sweating. You plug in a new hardware, and the screen remains black. A quick look at the debug port confirms your fears, kernel panic, and consider yourself lucky for this. It could be worse. It could be black, and that's it. So, this is when you start questioning about your life choices. But please take a big breath, and yes, channel, if you can, your hitchhiker guides to the galaxy, and don't panic. Because in this next session, we are going to walk through what happens when you want to bring up AutoSD on your own hardware, not just a fancy supporting dev board. We'll explore when hardware just works, because may be unbelievable, but it can also happen. When you need to use BSP or out-of-tree modules, and how to actually make AutoSD support your platform the right way. So, we even have a decision tree coming up. It is not to confuse you, but just to show you the path forward, no matter where you start. Because in AutoSD, hardware enablement is not magic, but it's totally doable. So, ready to navigate this journey without panic? Let's start with the big picture, literally. What option you have when you're facing a new hardware? So, we are at this big picture. This is your choose your own adventure moment. You got a new board or SOC, and you are thinking, can I run the AutoSD on this? Let's walk through this decision tree. Your first question would be, is it already supported by AutoSD? And if yes, congratulations, you won the jackpot. You can just download the image, boot it up, and voila, plug and play. It is not just working, it is blessed. But maybe you are not so lucky. And the next question would be, is your hardware already upstreamed? Here's where things get interesting. AutoSD follow the upstream first rule. If your code isn't upstream, it won't be included. But if it is upstream, you got a shot. So, upstream code doesn't mean it is already enabled or maintained in AutoSD. That's where you come in. You can say, hey, I want this hardware fully support. I'll help to maintain it. Great, submit a patch, and now your AutoSD has a new home. Your hardware has a new home in AutoSD. But remember, ownership means responsibility. If you bring it in, you help keeping running. Contributing means taking care of your code over the time. But what if it is not upstream, which means that you are in the node branch? So can you consider yourself doomed? Absolutely not. But you can just add the BSP code into AutoSD directly. So we got to have some workaround for this. And you basically have two of this option. The option one is the so-called Frankenbuild, which means you take your vendor BSP kernel, you take the AutoSD user-landed tools, sew it together, and give it life. Boom, you have a Frankenbuild. It is not pure AutoSD, but it works like it talks like it. It is perfect for evaluation, quick demo, or checking compatibility. The other option you have is the option 2, backport the drivers. Want a full AutoSD experience with a kernel tested and updated? You can backport your drivers from your BSP to the AutoSD kernel, and then build them as out-of-tree modules. It is more work, more elegant, and it pays off when you need something closer or even meant to production. Wrapping up, so whether you are on the express line or in the scenic route, you got option. And in the next slide, we'll unpack in details these paths. So, your hardware is already supported. Congratulations, you are on the fast lane. Build your image with Automotive Image Builder, or just grab a pre-build nightly. Flash it, boot it, and you're off. No driver digging, no patching. This works best for popular dev boards like Raspberry, QEMU, some Renesas board, and some automotive Qualcomm SoCs. So, enjoy the smooth ride while you can. Here's why plug and play with AutoSD is such a joy. AutoSD comes with pre-enabled driver and tested kernel config, aligned with user space, so your image inherits a setup that just works. You are not tweaking, patching, or praying, you are just prototyping. Let's break it down. As pro, you have a fast way to test, no kernel digging, and backed by the AutoSD team. As con, you have that your SOC may be mostly right. You know that V1, V2, V3 of the same board. I could tell you a story about this. And you also may have performance that needs to be tuned. But in general, yeah, life is great when your hardware is in the green zone. But don't worry if it's not. We got a way for that too. So, your hardware is almost work with AutoSD. It is upstream in Linux, which is a great start, but AutoSD doesn't ship it. Here's where things AutoSD follows the Red Hat upstream first policy. That means no downstream drivers, no matter how shiny they are. But if you driver already upstream, you can help move it officially. Submit a patch to the CentOS stream kernel repo, test it, and maintain it over the time. Because here's the key idea. With a great contribution comes great responsibility. If you send it upstream, you help keep it running. So, if you want your hardware to be part of the ecosystem, give it a good home and a bit of maintenance love. So, let's say we got upstream driver, you are motivated, and you are ready to make your AutoSD driver official. Great. But before you submit the patch, let's talk about what this really means. First rule, no core image hacks. Your driver must work as loadable module. If it needs patch just to boot, we're gonna hit break. Second rule, stable ABI helps, but they are not magic. Most things keep working, but you are the guardian of your driver. If the kernel change goes your driver rogue, it's on you. Keep it on the right way. And now, what happened in the no branch? Let's look at what the BSP option bring in. So, why grab the BSP kernel? It is the fast way to see AutoSD into new hardware. Your vendor starter kit gets up and running in hours, not days. And this is great for demos and early validation. But here's the catch. BSP from a few major pitfalls. First, they are frozen in time, no update, no security patches, not even a brand new SOC, often shipped with a kernel already several releases old. Second, watch out for code drifting, mismatched with AutoSD user space. As we like to say, using BSP in production is like duct taping your car airbag. Clever now, dangerous later. In any case, if you decide to use BSP kernel, at least bootstrap it smarter. Rebuild it with the AutoSD kernel configuration, and so your BSP speaks the same language as user space. Remember that BSP are proof of concept for quick test. For anything that passed the demo, please plan to move to out of 3 modules. We've seen how BSP can help things off the ground, but now let's talk about what happens when you try to fly long distance with them. Let's lay out. BSP don't follow any update cadence, and definitely not the AutoSD. They don't get maintenance, they don't get security patches. Your AutoSD is a moving target, your kernel should be too. That's the current message here. So use BSP, play with them, and bring your board up, but don't treat them as a long-term solution. Let's say that if your RD has the permission of taping things, just promise that your operation won't. Now, you try your hardware with BSP, it booted, it worked, and it even blinked some LEDs. Great. But now you want to go from proof of concept to near production grade. Just remember that for production grade, the code must eventually be upstreamed. In any case, if you landed here, no upstream option is viable. That's where out of 3 modules came in. Think this option like installing custom part on a factory vehicle. You are not reinventing the engine. You are just adding what you need in a clean and supported way. And here's how it works. You keep using the AutoSD kernel, which is tested, trusted, and maintained. Your drivers are packaged, installed externally in the KMS style. As long as you follow the AutoSD kernel ABI rules, you are good. AutoSD is designed with stable ABI in mind, which means that your modules are expected to remain compatible across kernel updates. This gives you a long-term stability without needing to get your code upstream right away. So, after trying things with BSP and liking the result, this is how to make your setup safe, easier, and maintainable. So, we are still in the case where your hardware driver isn't upstream, but you want to run AutoSD rebuild, and you stay close to the main line. As we saw it, out of 3 modules is your path forward. The flow is quite simple. Start the official AutoSD kernel source. No need to rebuild it. Use the published kernel headers. Build your driver modules against the headers. And use the automotive builder to add it to your image. Now, let's be honest, this isn't completely free. You need to maintain the module, you test and validate it, and the community probably won't give you any support on this out of 3 code. But, and there is a big but, in return you get a stable ABI, so your driver won't break on every update. you stay aligned with mainline using a secure and safe kernel. It is faster to get testing, and it is a realistic solution, especially for vendors or startups that needs the hardware to work now. We are finally out of the hardware madness, but we still need to recognize that from boot to brakes, modern vehicles rely on software almost as much as hardware. And the checklist on the screen looks familiar: airbags, brakes, seat belts. But now we have to add something new: a reliable and maintainable Linux stack. So, modern cars are basically rolling data center. The days of just engine and wheels are gone. Today is more ECU, sensor, containers, and networked services. AutoSD fits this because it was designed with these realities in mind. Specifically, there are three big reasons why. Safety and isolation. Breaking your system shouldn't crash because infotainment consumed all the memory. Mixed criticality means that your system organizes and recognizes that not all processes are equal and discriminates between them consciously. Continuous update. AutoSD is a stream distribution. No version, just nightly and cute Git hashes. When we say that AutoSD is safe, we are not just tossing around buzzword. AutoSD is upstream for a project that is the Red Hat ISO 26262 certified in vehicle OS. This means that components are selected, built, and maintained with functional safety in mind. Updates use OSTree. Safety also means isolation, and here containers help. On top of that, there is BlueC, a runtime layer that orchestrates safe containers and enforces isolation policies. And last but not least, the kernel itself is real-time tuned. Everything is producible and traceable. And behind all that, there is a community with safety mindset. Let's talk about one of the trickiest problems in automotive system, mixed criticalities. Running safety critical workload next to non-critical ones without interference. Think of this like an airport airways. Some vehicle, like your emergency brake system, needs absolute priority, while others, like infotainment, can afford to wait a bit. Strict isolation. QM partition lets you wall off safety workload in container style. State manager that provide a way for middleware and OTA system to understand and respect domains. No guessing, no hack. The point is, AutoSD knows that this system is not just single-laned, it is a multi-lane highway. And think about the software release. Think of AutoSD as a live Linux pipeline built on CentOS stream, so every upstream change flows in as soon as been accepted. That means you are not waiting quarterly version or partial rollout to get an update. And this is the commercial cousin.
I'm not the commercial cousin, but the Red Hat in vehicle OS is. So basically, it's easier for me to move here better. So now I think Alessandro introduced, he explained, how you can use AutoSD as a community development framework. And, he also explained that it is designed, for, to support automotive use cases. In this section, I'm presenting 3 slides because you may want to know effectively, what are the features of these, commercial housing, why should you use, AutoSD as, development framework? Why would you want to bring up new hardware on AutoSD? Why would you want to contribute, right? Now, this is how, so basically this is the system level architecture of the in-vehicle OS 1.0. And, here you can see the safety scope and how we support mixed criticality. As Alessandro already mentioned, the in-vehicle OS is already certified as a safety element out of context up to ASIL-B, according to the ISO 26262 second edition. And basically here on the left, we have, yes, you can see the cursor. So on the left, we have the host partition where safety application can run. And on the right, we have the QM partition. So the same model is architecturally enabled on AutoSD. So in AutoSD, you have the QM partition where you can prototype running QM workloads. And you have the host partition where you can prototype running ASIL-B workloads. And in the vehicle OS, we offer a subset of the glibc as, to be ASIL-B certified to support safety application. And in the QM partition, everything else, any other, package that is available in AutoSD. And mixed criticality is claimed, between user space workload is claimed by leveraging containers. So here we have, a nesting of systemd at Podman that is supporting an isolated QM partition that is an isolated container. Inside this isolated container, there is another instance of systemd and Podman to allow sub-containers and to prevent QM processes from sending spurious signal to this, baseline of systemd. In the kernel, we have, ASIL-B kernel functionalities, subsystems drivers that support ASIL-B application, and then we have the remaining active kernel code that, yes, can interfere with everything else. This bad guy here can interfere with the kernel components on the left. It can also interfere, with the user space processes. However, we have, dedicated safety mechanisms and verification activities that are aimed, to support this non-interference claim. And the current certificate is, hardware dependent because, we don't believe it is possible, to qualify an operating system in a hardware agnostic way. However, due to the scalability of the kernel, as you know, it is pretty straightforward to move from one hardware to another. However, to do so, it is important, to have this hardware supported in AutoSD. So this is one of the reasons why you may want to start prototyping new hardware on AutoSD and try it out. And the main system level safety claim are that, that ASIL-B glibc API reliably perform their functions in accordance with the glibc specification. So, and that the in-vehicle OS is able to support mixed criticality by using a QM partition, and this is a way to restrict interference from QM application to ASIL-B application. And indeed, the Red Hat in-vehicle OS publishes a hardware agnostic programmable interface. not because there is anything special. This is just the way Linux is designed. So the programming interface of Linux is hardware agnostic. The implementation is hardware dependent, okay? And this is the reason why the certificate is hardware specific. And then here we have the main system level assumptions of use. So we don't, in Red Hat, we don't require to have important monitoring mechanism like, hypervisor or similar. We demand to have an independent watchdog, because even if we have real-time capability, so as Alessandro mentioned, AutoSD comes with real-time tuning and tools. However, we believe that given the complexity of the hardware that the vehicle OS run on and the complexity of the overall software stack in general, it would be really, really hard to make a real-time safety claim without a monitoring hardware watchdog, okay? And indeed, we have the assumptions of use on the glibc functional specification. So the user shall use the glibc doc RPM as a reference of the functional specification and implement his application accordingly. The vehicle user shall comply with the safety manual of the hardware. This is trivial. And also the target hardware platform must be ASIL-B or higher, indeed. And from a safety architecture, I already introduced this. All QM application must be confined to the QM partition. And there is a subset of usable glibc API that can be used by ASIL-B application. And the vehicle OS and user shall not link application against their own private version. This is also trivial, like otherwise you're using a different version of the libraries. And the end user shall use the pre-built binary. So in fact, it is not by coincidence. AutoSD also is a binary distribution. So we deliver ready-to-use binaries. Alessandro explained how to customize these binaries before submitting patches, how to work with out-of-tree drivers. However, our deliverable is binary. And indeed, the firmware must be also ASIL-B or higher, because otherwise it will, all the safety claim from a system level would fall apart. And that's it. Now, I don't know if we have, maybe we have some minutes for questions. I don't know if it was Chris or you. Now it's closer to Chris.
I have a question to the software stack slide you showed.
Sorry.
Yes. Yeah, that one. So typically you would have an Ethernet IP that is QM with an Ethernet driver that is QM, and then the application would wrap the data with an end-to-end library and treat the communication path as a gray channel. Mm-hmm. And in this diagram, where would you execute the QM Ethernet stack? Because it has to be accessed by the ASIL-B application, but you said all QM has to go into the QM partition, but then I can't understand how it works.
So, no, I understand your, I think here the networking is ASIL-B, because for the, this is also customer driven, right? So we have a reference system on chip that we are targeting, okay? And for that system on chip, I think the networking was qualified as ASIL-B or higher.
So you say you have an ASIL-B Ethernet stack?
Yes.
Okay.
Yes.
And an IP.
And an IP, yes. So, but this is, the reason behind this is simply business driven. So it is, we picked, our initial partner, and and that this is what drove this choice. But I understand your point. I mean, so you say usually if the networking was not qualified as ASIL-B, so if it was QM, then it would sit on the other side here on the right. So whatever you see here, this is basically, these are components that are qualified as ASIL-B functionally. So basically to functionally behave as up to ASIL-B. Whatever is here on the right is qualified to non interfere with the rest of the kernel code and with the user space up to ASIL-B. Yeah.
Okay. So thanks a lot for the presentation. I have two questions. So one is related to this. In this slide, you mentioned scheduler is also on the safety side.
Correct.
So like do you have like a safety claim on the Linux kernel scheduler itself, or do you mean like by some monitoring mechanism or independent?
That's a good question. So usually when people think about the scheduler, they think about meeting timing constraint, right? Okay. That's not just about it. Okay. The scheduler is also responsible for context switching, so for saving and restoring. Yeah, exactly. And that is pretty dangerous. When you save and restore the context of your process that you run, if you corrupt data, then you are in a big trouble because you will, corrupt whatever you have on the heap, right, or on the stack. So, and that would cause, that would have dramatic consequences. This is probably the main reason why the scheduler is qualified as ASIL-B. And because, as already explained, if you had to make a time safety claim, so a real-time safety claim, first you should not look just at the scheduler. So everything, all the code when executed, contribute to the delay, but the problem really is that, as I already said, really the complexity of the hardware underneath. So it is in the common system on chip, NXP, Qualcomm, NVIDIA, whatever, right? No, I can name anything, right? So they are very, very complex. They have, they have many level of caches, and there is DMA, and so there may be many different situations that would lead you to violate an FDTI.
So like the normal Linux scheduler, like you guys just did the qualification of it? Like,
yeah,
okay.
yeah. The preempt with, we basically compile the kernel with the preempt-RT, configuration, and yes, we have some schedule. Now I cannot disclose the detail of the safety manual, but we have scheduling policies that are usable.
So just last question.
Yeah.
Also, it's on the same slide, you mentioned like some subset of glibc is available for
Correct.
the safety app. What about C++? Any standard library?
It's on the roadmap. Yes. So.
Yeah, thank you. If I remember correctly, ISO 26262 for ASIL-B requires 100% branch coverage with tests that are requirement-based. So my question is, where did you get the requirements and where did you get the tests to achieve this on the kernel?
Well, there is. Yeah, I should give I should give a different presentation that talks about the Red Hat methodology of, to achieve ASIL-B. I will give that at the Eclipse SDV process. I don't remember the name. There is a working group on September 1st. So if you can join that.
No,
but
I cannot. But
the short answer is
you have the requirements and you have the tests, right?
Correct. So we don't. Okay. So for the current in the current methodology, we don't measure code coverage, so we don't use code coverage. We leverage on alternative data, like reliability data coming from RHEL, and we have a tailored, process. Now, where do the requirements come from? mainly when it comes to the glibc, mainly from the glibc specification, and that in turn also refer to the applicable standard.
I was more worried about the requirements for the kernel rather than the glibc.
For the kernels, we mainly test the kernel from syscall. However, if I remember correctly, we leverage the maintainers and the maintainers' judgment, and also the currently available documentation enhanced by the maintainer judgment that we have internally read at.
I have a question about how you detect or prevent that QM application will interfere with AZB application when they use common modules of the kernel. So,
when
for example,
now that's a good question. Yes. So we have now we have a dedicated verification campaign. Okay, that is used basically that is aimed, to claim freedom from interference. That is based on heavy stress testing through syscaller plus Kazan enabled. So there is basically a dedicated verification campaign that leverage thousands, if not more, many thousands of hours
let me make
of fuzzing. Yes.
Let me make an example. So let's suppose that you have your QM application that want to use network or file system, but you have even QM application that will use network or file system.
Correct.
Okay, so let's solve this. One of your QM application is stressing your file system and will lead to have interference in terms of timing to your AZB application that won't watch the file system, because the file system will be always locked by QM application,
Yes.
and it will not get the service that you want.
Yeah.
So how do you detect these kind of things? Do you have some safety mechanism?
For timing, we have the external watchdog, so that will be detected anyway. But the hazard would be if there was an abuse, if it was possible to abuse and corrupt the internal structures of the kernel from the QM application. And for doing that, to claim that that doesn't happen, what we do, we have like a very intensive stress test campaign that fuzzes for many hours across all the syscall from the QM partition, also with Kazan enabled to verify that there are no violation of dynamically allocated memory. And also, we also verify, as these stress tests run in parallel, we also have the functional test from the ASIL-B partition that runs continuously to verify that they continuously pass.
In the particular scenario that you describe, there are additional policy of rate limiting doing that.
Can you say more about this dedicated safety mechanism, point 3?
I don't remember. I don't remember the slides that I have for Eclipse SDV. Not today, but...
Maybe another question then. This test testing, how is it compatible with the fact that probably you have other space layout relocation? So stress testing usually tends to analyze a subset of a configuration, because stress testing is inherently not exhaustive. But if at the same time you have also randomization of where things are located, basically you have two competing scenarios where one tries to provide the coverage of a certain configuration, and the other one, the randomization, changes the configuration. So are you disabling, for example, other space layout randomization?
I don't know. I need to look. I mean, that is driven by. I mean, to answer you, I should. First, I don't know if I can answer you like for in terms of confidentiality, but I don't have the technical answer because I'm not in charge of the the detailed so I don't know the answer. So in summary.
Okay.
Yeah. So maybe. It's related to what already was asked. So there are two things that we talk about when we talk about safety. One is freedom from interference, right? That means that there is a higher priority task, SLB or something, right? And when it is running or it wants to run, the QM partition does not come and block it. The QM application does not come block it, right? Or if the QM application is running and SLD wants to run, it can preempt it. This is one thing, right? This is freedom from interference, right? Second thing is about the corruption, like you said, right? When the scheduler question was asked, that if QM partition and SLB partition are talking to each other, right? The QM partition does not corrupt it, right? What you explained is that maybe on a qualified hardware, right, and some proprietary solution, you have solution for both of them. Is that understanding correct?
Yes. So the QM partition. So basically, you can use namespaces and C groups to tune the amount of resources that are usable from the ASLB partition and from the QM partition. So in that regard, you enable the availability of your system, because if anything goes wrong, if you get preempted, if you have a temporal interference, there is the washer. But you don't want that to happen, because otherwise you will be a very upset driver. The watchdog triggers, the car pull over with a fallback MCU, and you are just there,
So you
now,
resource limit the QM application.
But exactly. So this is how this is achieved. Now the other question was like inter-process communication.
Yeah.
Right?
How does, if they are talking to each other, how do they do not corrupt each other?
For not corrupt. So it is possible. There are there are possible inter-process communication between ASLB partition and QM partition, and here there is not magic. I mean, there is no magic recipe here. So
you depend on hardware.
Not even. You depend on the application, because you need to know that once you have a channel that is open between the ASLB and the QM partition, then you need to know that whatever data is coming from the QM partition, that is not to be trusted. Okay, so in that case, as Chris was mentioning earlier, you may adopt a system-level end-to-end mechanism that would allow the host partition to check the integrity of the data coming from the QM partition, assuming that this data is coming from another entity that is ASIL, right? So the question is, why would an ASLB application consume data from a QM application? So either you need this data for a safety-related application, for a safety-related goal. In that case, you need to have an end-to-end, and the other sender must be qualified as ASLB or higher. Or you may have this data for something that is not safety-related, but then you know that this data is not contributing to any safety goal, and the safety application, you will use it for something else that will not, at the end, interfere, but not interfere like architecture, like for the way that this data is used. Oh yeah, now we are out of time. Thank you.